start करना है from the Schrodinger equation of the wave function, the quantum mechanics, the wave nature of the particles. We know that the Schrodinger equation, let me just write this, Schrodinger's equation of motion is Schrodinger equation of motion of a quantum particle is iota h cross curly by curly t of psi equal to minus h cross the square upon 2m curly square by curly x the square plus v into psi. This is the Schrodinger equation. Now psi is a wave function describing the quantum particle. For a quantum particle in one dimension, we have, suppose that dimension is x, we have, this is x, just take it as x, and t here. Psi is a function of x, that is one dimensional x-axis. We have just taken that dimension as x-axis, and t is the time. So wave function of the particle is dependent upon the path it follows and the time that is passing through. So the wave function will change with respect to time also. And the potential, now wave function of course travels in a potential. So potential is also, as a wave function is traveling in one dimension, so the potential energy is also in one dimension, and it will also depend upon time t. So these things will change with respect to time t, and psi is x comma t. Now we know that the wave function is time dependent. Here up we can take also time independent, but time independent, that is psi, if it is not depending upon time, let me just write it, correct it here. If it is not depending upon time, depending only upon this thing, that it represents, what it implies to us is the stationary energy states of wave function. By stationary states, like for example in quantum mechanics, for the hydrogen atom there are stationary states. So this type of the wave function represents a stationary wave function, that is a wave function which does not change with respect to time. Wave function that is not changing with respect to time, of course it will remain as it is. As the time goes, it will only depend upon the position, that is on the dimension, that is x-axis. So this kind of a wave function is used for the stationary, or another word is degenerate states. Not only energy, other properties also. So it represents stationary states, we can say that. So this is the wave function for that, but here we have taken the wave function that is depending on time also. So this is the wave equation where this term is called as the Hamiltonian operator, H cap. This is Hamiltonian operator. This operator gives you the value of energy when it is applied on the wave function. When it is operated on the wave function, it changes the wave function, and the resultant value is the actual energy state. It is the energy state of that wave function. So it is the energy operator, a Hamiltonian operator. It gives the energy value, not actually the energy. So it gives the energy value, energy state. So this is the Hamiltonian operator, and this is the potential energy you can see here. and this term, this is the potential energy you can see here, and this term, let me just write it like, yeah, now this term, you can see this term, is actually the p square upon 2m, where p is the momentum operator. Here p is the momentum operator, which is curly by curly x, the the thing that is changing is the curly by curly x in p. So this term is the this 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 term this term is the momentum operator, and dividing the momentum, the square divided by 2m, is actually energy. We know that. And this energy, how do we know that this is the energy? This is the energy in the case of non relativistic case. That is the case when we are considering a wave function. Let me just write it here like, wait, this is, suppose this is x-axis, take it, all right. Let me just write it again. Yeah, no, it's fine. This is the x-axis, and so let's just, this is the y-axis, and this is the z-axis. So it's just a coordinate system. You can understand that simply the three-dimensional coordinate system, a Cartesian coordinate system. We have a wave function in this coordinate system. This, yeah, right. This is the wave function. This is representing psi, all right, x and t, and is representing quantum particle in space time. Not only space but space time. We cannot consider the time. Time is has a direction in every direction. That is a simple case, but we can only construct the coordinate system for the three dimensions. For the taking the time as the fourth dimensional is a concept that time has direction in every direction. So we cannot actually define the specific dimension to that time. So it's just considered as the space and time. For more concept on that, we have the special theory of relativity and general relativity. You can check that out also. So this is a wave function in a three-dimensional coordinate system in space time. So psi xt is representing that wave function. When this wave function is moving, not only in this direction, in any direction, you can consider this direction or any direction in space, then when it is moving not near the speed of light, very is in a normal speed, everyday life, like in an everyday speed that you see about, like the car moving on a road, the car going on a road or anything. So in a normal speed, not the speed that is v, suppose it has a velocity v, which is less than c. V is less than c. C is the speed of light. So in that case, this is a non-relativistic case. The kinetic energy of this quantum particle is given by E is equal to p square upon 2m. And this term is representing the kinetic energy. This term is representing the kinetic energy. This term representing the potential energy. So this is the whole energy operator. Now this is just an operator. Differential curly square by curly x square is the second derivative of a term of a function with respect to x. That is the spatial coordinate. So this whole term represents the Hamiltonian operator. It's just the concept that gives you, when it is applied on a function, it gives the value of energy of that function. A function is a quantity that has variables and is dependent, and it has every specific value at every point. So when this is a wave function, this describes the wave particle, quantum particle. So when this wave function is applied here, so it gives the energy value of that operator. And this is the left hand side. We have iotagicals curly by curly t of psi st. This is the time evolution of the wave function. How wave function will, the value of the wave function wave function will change with respect to time as the time passes. So this is a pretty much concept about this Schrodinger equation. Let me just take it down. Yeah. Now in this Schrodinger equation, let me just write it again here. Yeah. Iota h cross curly by curly t of psi xt equal to minus h cross the square upon 2m, yeah, curly square by curly x the square plus vxt the whole multiplied by psi of xt. This is the time dependent Schrodinger equation. So first of all, what we found is that this is the non-relativistic Schrodinger wave equation. Schrodinger wave equation, and of course, as it has only one dimension is considered here, and only time, and only the one dimension is considered here, and therefore this equation is for a particle in one dimension. Notice one thing here, as we are discussing the quantum mechanics at the MSc level. So in MSc, the wave function can of type this and x and t, where psi xt represents the wave function in one dimension, but wave function is a three-dimensional in for a particle in one dimension, but a particle in three dimension we have previously written that in terms of position vector r vector t. This is the wave function in three dimensions, taking the Cartesian coordinate only. The position vector r vector is xi cap plus yj cap plus zk cap. You know that. But there is another way we can write this thing. In this thing in three-dimensional, in MSc we often use, instead of writing r vector, we write it as x vector comma t. This one thing that you should notice, that is really important to note for you, is that we even use this notation. It's just a representation, and so you should, this is not a small level. You will get higher and higher. So this is the more simply understandable concept, and it has important understanding the quantum mechanics in details. So this notation is also used. So you should understand this thing also. So first of all, we understand that this is the non-relativistic Schrodinger wave equation. So it's not the general wave equation. Because as the wave function approaches the speed of light, as the wave function approaches the speed of light, we tends to see, as we approaches the speed of light, then what happens, like in Large Hadron Collider? What happens in Large Hadron Collider at CERN in Switzerland, in Geneva? We accelerate the charged quantum particles like the protons and the other particles, and we bombard them, collide them with each other, and study the energy distribution and energy emission and the another particle emissions. So in that cases, at a Large Hadron Collider, you can check that out on YouTube or Google. The velocity is near to the speed of light of a quantum particle. So in that case, the Schrodinger wave equation, we won't have p square upon 2m quantity. Instead of that, we will have the relativistic energy. Relativistic energy, which is given by under root of p the square c the square plus m the square c the power 4. This is the relativistic energy. So it's just a simple concept. Let's just take it. So first of all, we have understood that this is the non-relativistic Schrodinger wave equation and it's for a particle in one dimension. Schrodinger equation represents that.